a lecture on momentum. The big idea of this lecture is the impulse momentum theorem. A speeding mass is mass times velocity, and it is termed momentum, symbolized by the letter P. Momentum P is a vector defined as P equals mass times velocity. If a mass is forced to change speed, m delta v is the change from the final speed from the initial speed, then we are changing momentum. Change in velocity, as we know, is caused by a force. Therefore, force changes momentum. Force is a change in momentum per time. This is another form of Newton's second law. This means mass is forced to change momentum. Delta P is equal to force times time. A force over time changes momentum. It is another form of Newton's second law. An impulse, a transfer of momentum to an object, is what we call an impulse, a delta P. Momentum is a vector. A change in momentum is also a vector, which we give a name impulse. The change in momentum is termed impulse. Impulse, therefore, is a vector that changes other vectors. This is the impulse momentum theorem. Newton's second law, force over time, changes often the velocity of an object, but it could change the mass and the velocity. That change in momentum we symbolize with the idea of an impulse. Let's say we have a truck, and the truck is heading towards a wall. The truck has initial momentum of its mass times its initial velocity, and the truck crashes into the wall, so its final momentum is zero. The force of the wall in a short time transfers the momentum away from the truck. The force of the wall in a short time stops the truck. If the same exact truck has the same exact initial velocity, therefore the same exact initial momentum, and it instead hits a haystack to be forced over a longer period of time, with less force in a longer period of time, to slow down, to stop, then its final momentum is also zero, stopped by the haystack. The initial momentum of the truck in both scenarios is the same, and the final momentum of the truck, nothing, in both scenarios is the same. Therefore, which has the greater impulse? Well, if they both start out with the same initial momentum, they're both the same moving truck with the same initial speed, and they're both stopped, they both have the same final momentum of zero, and their change of momentum, their impulse, is identical. Impulse is not a force. A big force in a short time created the same impulse as a small force over a long time. Here graphically I'm showing you that an impulse, a change in momentum, relates both to the force in time and the change in velocity of a mass. We can get the same impulse, the same change in momentum, the same transfer of momentum in the top figure with a force over a long time, as we can in the next figure below, as a force of twice as much in a time is half as much, twice the force, twice the time. Gives us 4 boxes of momentum as the top rectangle of one force over 4 periods of time. Gives us a value of the same momentum, let's say 4. Or 4 times the force in 1 unit of time gives us the same impulse, the same transfer of momentum. All the rectangles, all the areas of these rectangles are the same amount of impulse. Mass times a lot of velocity, or a lot of mass times a fourth the velocity, or double the mass and half the velocity. We get the same amount of impulse in all different cases. We can visualize what's happening when we're talking about impulse. Here, from your textbook, a person is kicking a soccer ball. We see their foot is making maximum contact in the middle figure, and then the soccer ball starts to leave the foot, and the foot is making less contact. We can graph the force over time of the foot on the soccer ball. We see when contact begins, the force increases until there's a maximum force, which is compressing the soccer ball. As the soccer ball leaves the foot, the force decreases, and the soccer ball goes from compression towards maximum force, and as the soccer ball leaves, the soccer ball expands. This all happens in a very short duration of time between contact beginning and contact ending. The area of the curve of force over time, is the impulse. Here we see a picture of a golf club hitting a golf ball, creating the same effect. A large force in a very short time is creating the impulse to make this golf ball go from rest to a great speed. That great force in a very short time to give us a large impulse has compressed even something hard like a golf ball. But the golf ball expands to leave the golf club, rather than just being squished and destroyed and staying where it is or breaking apart. It's an elastic object. Microscopically, the object hitting the ball, we can think about the ball as a bunch of atoms and molecules attached, bonded together on springs. The ball, as it's being compressed, the atoms are coming closer together. The springs that connect the atoms, the electrical attraction, gets compressed. And when you compress a spring tries to restore itself to its rest length. The spring doesn't like to be compressed. It expands again, if you will. And so the ball compresses from the maximum force of the contact object from the foot of the golf club. And the springs, the electrical attractions and repulsions, the bonds between the atoms and molecules, expands again as the ball leaves. This happens in a very short period of time, as we see on the graph, from a very large force of compression to a maximum, and then as the contact ends, as the ball leaves, this all happens between 30 and 70 milliseconds. In a very short time, we have a large force. The area again on this curve of the maximum force in a short time is the impulse. But since this force is changing over time, we can describe the impulse by the average force over time. And that's what the equations that we were seeing were, the average force over time. What is the average force here? It's half the maximum force, or 400 newtons, times it by 30 milliseconds, 70 minus 40 milliseconds. 70 minus 30 milliseconds. So the duration of 40 milliseconds, 70 minus 30, times it by the average force, half the maximum, of 400 newtons, gives us the impulse, the area of that curve. This is shown in this graph here. We can take the maximum force divided by 2 to find their average. And the rectangle of the average force times that same duration of time, average force times time, is an impulse. Let's see how this works. Here we have a force applied to a hockey puck of a half a kilogram. The puck slides to the right at 10 meters per second. It is hit with a hockey stick that exerts the force shown. What is the approximate final speed? Since the force is changing from compression to max to back to minimum as contact ends, we'll figure out what the average force is, 25 newtons over the duration of time from 10 to 30 of 20 milliseconds. 25 newtons times 20 milliseconds will be our impulse. We have an impulse of a half a kilogram times a meter times seconds. There is no named unit for an impulse. Previous classes have called the unit of impulse chucks, after Chuck Norris. Since a force times time is an impulse, as is mass times change in velocity, then this mass of this puck of a half a kilogram is being changed. The velocity from final to initial is being changed. We're told the initial velocity is 10 meters per second. So if the impulse is 0.5 kilograms meters per second, or a half a chuck, and it's a half a chuck on a half a kilogram object, whose initial speed is 10 meters per second, we can figure out the final speed is 11 meters per second. Just solving that equation for V final, knowing V initial, knowing the mass, and knowing the delta P. It's reasonable to think a hockey puck that gets hit in a short time with a big force increases its speed from 10 to 11 meters per second. Those are reasonable speeds. Answer this question about finding the area under the curve to relate to impulse on a blackboard. Here we'll again use the impulse momentum theorem. Answer this question on blackboard. Keep it simple. Similar question, where our astronaut here is standing in for the thrusters on the astronaut acting as the rocket. Use the impulse momentum equation again to answer this question. Answer this question also on blackboard about a car that applies the full force of its brakes by slamming its brakes, but it slams its brakes at twice the speed. How much distance will increase when the full force is applied over an object, a car that's moving twice as fast? Answer this question about, again, a rocket lifting off of a certain weight to attain a certain speed. So our small rocket of 1,000 kilograms is trying to attain a certain speed. How much force is needed with this knowledge? Answer this question on blackboard. Now we'll get to the idea of what momentum conservation means. An object is falling towards the Earth. As it's falling, gravity is increasing its speed. The force of the Earth on the apple, the force of the Earth on object A, over time is increasing the speed and therefore increasing the momentum of the object. This would be an open system. The force of the Earth is affecting the change of momentum of our object, of object A, of the apple. It turns out that the Earth has an equal and opposite change of momentum, an equal and opposite transfer, an equal and opposite impulse. The force of the Earth on the object A, the force of the Earth on the apple, has an equal and opposite force of apple on Earth. In the same time frame that they interact means they have equal and opposite impulses, or equal and opposite changes of momentum. This is momentum conservation, equal and opposite changes of momentum. In a way, this is where the third law from Newtonian mechanics comes from. Equal and opposite forces over time give you equal and opposite impulses, which gives you momentum conservation. So the third law, in a sense, comes from momentum being conserved. If I add up the two impulses, the net impulse, net delta P, is equal to 0. Momentum is conserved in this system being object A, the apple, and the Earth. These are only two interacting objects. I've enclosed my two interacting objects. This is my closed system to see that momentum is conserved between these two interacting objects. But it's important which system I pick. If I just look at the object, the ball, say, that's falling towards the Earth, then it's open to the external effects of the Earth. The force of the Earth is having an external effect on just the system of the ball. Momentum is not conserved in the open system, open to external forces, external influences, in this case from the Earth. On this ball, the momentum of the ball is not conserved. The momentum of the ball and the Earth total is conserved. So if my system is ball plus the Earth, then in that system of two interacting objects, momentum is conserved. Answer this question about what type of system you pick and when is momentum conserved on blackboard. We'll use momentum tables to keep track of the momentum of an object initially, the initial momentum, and the final momentum, and the impulse, the change momentum. If object 1 and object 2 interact, then we'll keep track of their initial momentum and their final momentum and see whether their change of momentum, their impulses, are equal and opposite. Thus we'll have a conserved system, a closed system, if object 1 and object 2 are the only interacting objects. We can keep track of the total momentum of the system before, initial, and the total momentum of the system afterwards, the final momentum of the system, which should be the same if momentum is conserved. This is our momentum table. It's keeping track of our momentum vectors before and after. Keeping track of these cells in this table is like playing momentum Sudoku. For example, a rifle shoots a bullet. The rifle and the bullet are initially at rest. Then the bullet is fired. This 10-gram bullet is fired with a final velocity when it leaves the rifle of 300 meters per second. What is the velocity of the 4-kilogram rifle after the shot? Let's fill in a momentum table to play momentum Sudoku. Initially, the momentum of the bullet and the gun, they're at rest. They have zero momentum. So the total momentum of the gun plus the bullet system is zero. If momentum is conserved, it means the bullet and the gun are the only two objects interacting. The momentum of the system before is the same as the momentum of the system after, zero. I know the bullet is 300 meters per second and it's 10 grams. Therefore, it has 3 kilograms times meters per second. It's got an impulse, it's got a momentum of 3. Therefore, the gun must have an opposite momentum of 3. It's a 4-kilogram gun. How do I make 4 kilograms into a total momentum of -3? Well, it must have 3/4 of a meter per second in the opposite direction as its speed, so 4 times 3/4 gives me a momentum of -3. For the bullet's momentum of 3 to add up for the system to still have zero momentum total. The system have zero momentum doesn't mean that there's no objects moving. It means the whole system, or the center of mass of the gun and the bullet, is staying at the same location. Now I've answered the question of the speed of the gun by keeping track of the momentum of the system. I can also figure out the impulses on the bullet and the gun in this trivial example. The impulse must be 3 to have a final momentum of 3 if my initial impulse is 0. Therefore, the gun, with its momentum of -3, must have had an impulse of -3 added from 0. If two objects collide, momentum is conserved if these are the only two interacting objects. You can see from the animation the momentums of the objects before and after will be the same. You will do an example of this in the ill. For each object, they have the same transfer momentum, the same change momentum, or equal and opposite impulses, whether they collide and whether they're different masses or not. Momentum is always conserved in a closed system. Answer this question about a cart hitting a wall and bouncing off the wall with an initial momentum and a final momentum. What's the best choice for the change or the impulse, the change momentum or the impulse? Here a car hits a wall, but in this case the wall can move. Say the wall is on a frictionless surface or on wheels, or can simply be knocked over. If our car is made of clay and crashes into a wall and sticks to it, versus if the car is made of rubber and bounces off the wall, which is more effective? Is the rubber car bouncing off the wall more or less effective in pushing the wall back or knocking down the wall? Answer this question on a blackboard. An object that sticks, such as the clay car or clay ball, to a wall, we call perfectly inelastic. Perfectly inelastic collisions result whenever two objects move off either at a common velocity because they stuck, or in simple terms, if there's a loss in speed, it's an inelastic or sticking collision. The opposite would be a perfectly elastic collision where objects don't lose their speed. We'll see next week when we do energy conservation, perfectly inelastic versus perfectly elastic. Depends on whether an object loses its kinetic energy, perfectly inelastic, loses its speed, or maintains its kinetic energy, perfectly elastic. There the fish caught a small fish, momentum is conserved in such an example, or train cars locked together with a common velocity, as the fish had a common velocity. When objects stick together, that's an example of an inelastic collision. Momentum is still conserved. They share momentum afterwards. Here are two train cars. Train car 1 will be moving and locking into a train car 2 that's identical but at rest. And to this question about the speed that the train car 2 has after the collision. You can visualize the answer. Train car 1 moves to lock to the identical same mass train car 2, which is at rest. They lock together, they share, these identical cars share the momentum. If they're identical cars, each one of them has half the momentum, therefore half the speed. Let's do this problem now. Jack stands at rest on a skateboard. The mass of Jack and the skateboard together is 75 kilograms. Ryan throws a 3 kilogram ball horizontally to the right at 4 meters per second to Jack. What is the final speed of Jack and the skateboard? This is an inelastic collision, where a ball is in a sense sticking to or locking to Jack and the skateboard, and they move together with a common speed. We'll fill out a momentum table and play momentum Sudoku. Jack plus skateboard are at rest, the initial momentum is 0. The ball's initial momentum is 4 meters per second with its initial mass. Initial velocity is 4 meters per second, which initial mass of 3 kilograms gives it an initial momentum of 12. Therefore, the momentum of the system is all in the ball, moving to the right. Therefore, the system has a momentum of 12 moving to the right. The total momentum of the system before is the same as the total momentum of the system afterwards, if this is a closed system. So we have 12 momentum, or 12 chucks, afterwards to the right, the final momentum of the system. But we know the total mass of Jack plus the ball, 78 kilograms, and therefore if we know the total momentum is 12, then 12 divided by 78 is the speed that both Jack, the skateboard, and the ball have after the catch. So therefore we solve the question, and knowing the initial momentum of the ball, and that they share the same total momentum and the same velocity after the catch, then the total momentum of the system is known. If the total mass of the objects that are moving together is known, then we have the total velocity, the final velocity, after the catch. We can fill in the rest of this table by momentum Sudoku if we needed to. The mass of the ball times that speed gives us a half 0.5 for momentum of the ball afterwards, and 11.5 momentum for Jack plus the skater, moving at that same exact speed as the ball after the catch. And therefore we can figure out 11.5 was the impulse given to Jack, and an opposite 11.5 was the impulse given to the ball. And we can see we add down the rows, 0 plus 12 equals 12, 11.5 canceled out by negative 11.5, equal and opposite impulses conserves momentum. Adding momentum down the third column, 11.5 plus 0.5 equals 12. And we add along the rows. 0 plus 11.5 is 11.5, 12 minus 11.5 is 0.5, 12 plus 0 is 12. We add down the columns and across the rows to see that momentum remains, that the additions worked out correctly, to show that momentum before, initially, and momentum finally can all be accounted for. Momentum works also in 2 dimensions and 3 dimensions and beyond. Here a cue ball hits the 4 ball and makes the 4 ball go off at an angle. But these are simply momentum vectors in 2 dimensions, and they work the same way. We can play a momentum Sudoku, put a momentum table, and see that this works the same. The initial momentum of the system is all in the cue ball going to the right. The final momentum of the system must still be the same as the initial momentum of the system that the cue ball had, all going to the right. We break up the components of the 4 ball's momentum, and we break up the components of the cue ball's momentum. The components of the cue ball's momentum, the white ball and the blue ball, the amount of momentum up, or in the y direction, and the amount of the momentum of the white ball, the negative y direction, cancel. The vertical components, or the y components, of the white ball and the blue ball after the collision cancel. And the horizontal components in the x direction, for the blue ball and the white ball, add together to be the same as the initial momentum of the system all in the cue ball before the interaction. For instance, here's the balls being shot off at various angles. we can see that the vectors still add up to be the same as the original vector. When we get to study energy conservation, we can see both the conservation of momentum and the conservation of energy, Ke for kinetic energy. We can track it and figure out the exact angle the balls will make. Rockets is an interesting example of momentum conservation. Anytime you throw an object, there's an equal and opposite impulse on the thrower. In a sense, the rocket is throwing the gas down, therefore the gas gives the rocket an impulse upwards. As the rocket gives an impulse to the gas down as it throws it, it gets an equal and opposite impulse upwards on the rocket. The more gas it throws down and the faster it throws down the gas, the more impulse the rocket gets upwards, equal and opposite amount. This is how a rocket can move through the emptiness of space, by expelling its fuel, its gas or its solid fuel. It's throwing it away, throwing it down, so it can keep on moving up in a sense. But in this example, both the velocity and the mass of the rocket are changing. The rocket is increasing its velocity by throwing away, expelling the fuel, and it's losing its mass, which is also increasing its speed. Answer this question on Blackboard.